Let's take a look at the idea here of applying double integrals in polar coordinates. First, let's talk a little bit about the reasoning behind it. Why would we want to do something like that? As a quick review, let's just think about what polar coordinates are. I have some point in rectangular coordinates, which I'm going to call the point xy. And I can convert these to polar coordinates simply by taking the distance from the origin and calling this r, and then thinking in terms of this angle theta, where this is 0 degrees, and like we would typically move a unit circle, although r is not necessarily 1. So I can say that this is also equal to the coordinates r theta. And then that gives me a relationship, because now I can think in terms of x as simply being r times cosine of theta, and then y, of course, will be r sine of theta. And we also have the relationship x squared plus y squared equals r squared. So when would we want to use polar coordinates? Well, let's draw a couple pictures here. Let's take a look at a couple of regions that it may be really nice to use polar coordinates. If I have something that looks like this, I'm integrating over this region, which is a circle, say x squared plus y squared equals 9 or something like that. Using polar coordinates would make this a lot easier. Also, suppose I had a region that looks something like this. Keep in mind I'm looking down at the xy plane. So perhaps something like this. Oops. That's supposed to have the same radius, although it's not quite the way I actually drew it. Let's see if I can fix that. Yeah, something like that. And then maybe out here like this, where this is maybe x squared plus y squared equals 4, and this outside one is, well, maybe the same thing here, x squared plus y squared equals 9. This would be pretty tough to do in rectangular coordinates. You could do it, but it would be kind of tough. Or let's suppose that we simply had something that looked like this, some kind of wedge out here. Where again, I can probably define these in terms of x squared and y squared. And let's just say that this distance here, this radius is out here is to 1, and out here is, I don't know, maybe to 3 or something like that. Now integrating over this region, that could be, like I said, well, kind of tough. So converting all of these into simple polar coordinates will really make life a lot easier in terms of actually trying to integrate. Now, each of these regions are really nothing more than polar rectangles, because I can say my rectangle, or I can define my rectangle as being the points r theta, such that, say, A is less than or equal to r, which is less than or equal to b. So there's the range of r. And then let's use alpha less than or equal to theta, which is less than or equal to beta. So this is the exact same way we defined a rectangle in rectangular coordinates, where I would define the range for, or domain for x and the domain for y. So this concept of the polar rectangles, this idea, is really which allows us to integrate, to allow us to do double integrals in polar coordinates.